Okay, so now we're going to get back to actually talking about physics, which will be nice. I think we had enough of an aside talking about chemistry. Also, I apologize for the just a mustache that's happening right now. It's not good. I don't know whether I want to keep it or not. I mean, it's a solid mustache, but it is weird by itself. Anywho, today we're going to be looking at electrical fields, very closely related to gravitational fields. So since we've already covered Newton's law of gravitation, we're just going to be translating those formulas over into our electrical field formulas. Okay? So, thinking about gravitational and electrical, like if we had two objects, okay? If they have mass, they experience a gravitational attraction, all right? And the further away they are, the less field you have, the more mass they have, the more field you have. It's a very similar relationship when we start talking about electrical fields, right? Except instead of being about mass, it's about how much charge the two of them have. The other difference is gravitational fields are always attractive, okay? There's no way to repel something with a gravitational field. It will always be pulling it in. That's why there's a negative in one of our formulas. A negative field is an attractive one. With electrical fields, it can repel as well. Like if both of these are positive, they won't want to be next to each other. It will have a repulsive force. If they're both negative, they'll both repel. If they're opposite charges, though, that's when they'll attract. Okay? So, when we're looking at gravitational fields and electrical field, the source of a gravitational field is an object's mass. The more mass there is, the larger that field is. Okay? The source of an electrical field is their charge. All right? So, since it has been a little bit, since we talked about electric stuff, charge symbolized by Q, measured in coulombs. Coulomb is actually going to be the name of the law here. So we've got Newton's law of gravitation, that F equals gmm over r squared. Very similar law describing electrical fields is called Coulomb's law. We'll get to that in just a second. Okay. So, when we're looking at field strength, okay, how strong a field is, for a gravitational field, it's G. Okay, it's how much you're accelerating from that. For an electrical field, it's E. Okay, and when we're looking at how we're finding these, right, it's based on the force that's being delivered. The larger the force is, the larger your field is, but they're interacting with different quantities. With a gravitational field, you can find that field by taking your force and dividing by the mass of something. Okay, so force divided by mass gets you gravitational field. This specifically would be what we call the weight of something. So weight divided by mass, you end up getting gravity. When you're looking at an electrical field, there will be an electric force, all right? But that field is again referring to charge. So your force divided by the charge that is in that field will give you your field strength, okay? Which means that when we're looking at field strength for gravitational stuff, you've got newtons per meter, all right, which ends up getting you meters per second squared. When you're looking at electric fields, that would be newtons per coulomb. Okay, so different units for these two fields, but they're behaving similarly. The larger the force is, the larger the electric field is. Okay. Now we're looking at a uniform field. Typically, we just think about G as a constant. All right. If we're near the surface of the Earth, it's 9.8. If we're near some other planet, it'll be proportional to how big that planet is. Okay. But if you're looking at gravity and you're near the surface of a planet, all right, this thing has a huge radius. Okay. So that means that near the surface of that thing, all these lines pointing to the center, all right, you look at them close together, they're nearly parallel. They're ever so slightly not in the exact same direction, but if you're close enough to the surface of a large object, that G is a constant. Okay? Now, if you wanted to find that, if you want a numerical answer, what you would need is your gravitational potential. All right, so we talked about that one a little bit in our gravity unit. We'll mention it again in just a second. And you'd be dividing by whatever height you're at. Okay? Now, as long as you're close to the surface, taking that gravitational potential dividing by height will end up getting you a constant for G. Okay? Now, looking at an electrical field, we talked about a constant electric field last year with plates. Okay, so if you've got a positive and a negative plate, there will be an electric field in between here, and it will be constant. As you get closer to one plate, it will be attracting you more. You're getting further away from another plate, it will be attracting you less. All right, and anywhere in between, the sum of the electric fields from those two plates will end up being the same. It ends up giving you a constant electric field in whatever direction. All right, remember that whenever you're drawing field lines, they're always drawn like, which way would a positive particle go? Well, if I put a positive particle in here, it's going to go towards the negative and away from the positive. And I end up with a bunch of lines pointing straight down. Looks a lot like if I were to draw a flat plane on the Earth, right, really close to the Earth's surface, and I was looking at the direction of gravitational field. Okay, so if we're looking at a set of two parallel plates, we can get a constant electric field as well. All right, so there, if you're looking at a constant field, it's just going to be the voltage between those two plates divided by their distance, okay? Which means that there is another way that we could represent the units of electric field. Instead of newtons per coulomb, we could also represent it as volts per meter, okay? So we've had a one-to-one relationship so far, just flipping out a couple of units and variables, right? We still got distances there, right? But instead of gravitational potential, we have voltage. Another name for voltage, potential difference. So potential to potential. It's still talking about a similar quantity. It's just this one's involved with electrical things, okay? So force to force, mass to charge, okay? So now looking at a spherical field, if you've got to find the force between two objects, and we're talking on like a planetary scale, all right, where it's not at a constant gravitational force, all right, you can find your force by using Newton's law of gravitation. Big G, rip little g, you will be missed. Big G times the product of our masses divided by our radius squared, okay? So looking at this formula, the further away from something you go, you will exponentially lose that force there. Like if you're double the distance out, you will have a quarter of the force. If you're 3 times the distance out, you'll have a ninth of the force. All right, so gravity dies off real quick as you get further away from stuff. All right, and directly proportional to the product of your masses. So the larger the two objects are, the larger the force between the two. This is finding the force from object 1 on object 2, and also the force from object 2 on object 1. All right, this is Newton's third law. If one object is experiencing one force, the other object will be experiencing the equal and opposite force. Okay, so we got a way to find our forces there. So translating stuff over, all right, mass can seemingly be replaced by charge, right? So thinking about the force between these two things, that force between two charged particles should be going up as the charge of each of those particles increases. Okay, so putting in Q's, Q1 and Q2, whatever the charges of our two bodies are, or our two charged particles are, okay? Radius, the further apart from each other they get, right? You've got that divided by d in there. The larger the distance between the two is, the less force you're going to get. But similarly, when you're looking at a non-constant field, this thing is going out spherically. It's an inverse square law. The further you get away, it's going to drastically have an impact on the force. So we're going to have another r squared in there. Now, our main difference, we can't use the gravitational constant. No more big G. All right, we need a new one. It is still a constant. We're going to make it a K. Okay? So, this is for finding gravitational force. This is our formula. We do need a number for K, so let's get that down real quick. So K is round about 9 times 10 to the 9th. Okay? Which is an easier number to remember than G, right? G was 6.67 times 10 to the negative 11. Doesn't exactly roll off the tongue. 9 to the 9th, though, that's easy to remember. Worth noting, the way that I'm writing this right now, just feels intuitive, going from G to K, M to Q, but keeping the formula roughly the same, right? It looks familiar, all right? There is another way for us to write this formula, and this is the way that the book would be giving it to you, because this K here is actually based on another constant called the permittivity of free space constant. So if we're looking at K, if we want a more precise number than 9 times 10 to the 9th, it is instead equal to 1 over 4 pi fancy E with an O. So that fancy E with an O, that is another constant called the permittivity of free space. So wherever we've got K, we could replace that with that relationship right there, 1 over 4 pi E to the O. So that constant right there, numerically, is, I always forget this one because I never use it, 8.85 times 10 to the negative 12th. Negative 12th. There we go. So oftentimes it's going to be given in this form if you're looking at any of this stuff from the book, just because that thing shows up later when we're talking about like magnetic fields and stuff. I find them largely interchangeable. 9 to the 9th is kind of an approximation. It's not quite exactly that, but it's good enough for government work. So I typically use this version of Coulomb's law because it looks like Newton's law of gravitation. Similarly, if we want to find our gravitational field, when you've got a spherical field, when it isn't constant, all right, you can do G times whichever mass you're looking for the field on, divided by r squared. Okay, so if I'm looking for the electric field, if it isn't constant, it's going to be E, all right? Instead of G, we have K. Instead of M, we have Q. So looking for the electric field around whichever charge is involved here. Okay, so that Q, make sure you're paying attention to which charge it's asking you for the electric field around. And then still divided by r squared. Okay, so we can translate this stuff over between these two pretty easily, right? Wherever there's an M, we put a Q. Wherever there's a big G, we put a K. Basically done, okay? Our next thing, right, if we're talking about potential, I'm gonna just erase what's up here. Okay, if I'm looking for potential. Okay, gravitational potential, we've got this phi thing. Phi equals negative gm over r. All right, basically it's the gravity thing missing an r. Okay, and there's a negative on there for a reason. Okay, because your mass is always going to be positive, your radius is always going to be positive, big G is always going to be positive, but this gravitational field is always attractive, okay? So if we're looking for that gravitational field, it should probably be expressed with a negative, okay? That's just how they express fields. Negative fields are attractive, positive fields are repulsive, okay? When we're looking at electrical, okay, we need a symbol for electrical potential. That's voltage. That's what that is, right? So V equals, okay? So now looking at transferring stuff over. Big G, just replace that with Coulomb's constant. Big K, okay? Our mass, electrical field, is not based on mass. It's based on charge. So KQ over R. I'm not putting a negative on there, though, okay? Whole reason I'm not putting a negative on there. If my charge is positive, well, that would be a repulsive field for any positive charge that I'm putting nearby. And you're always treating electrical field as what it would do to a positive charge. Okay? So I want it to be repulsive. I want a positive number from my electric field and my electric potential when I plug in a positive Q. Okay, so I don't want that negative there. Now if I plug in a negative Q, right, remembering this electric field is always based on what it would do to a positive charge. If I put in a negative Q, I'm left with a negative number for my voltage. That means it is attractive to positive charges. Okay? So we're not going to need to worry about putting a negative on this formula simply because the attraction and repulsion from this field is implied by the charge itself. Okay? we know whether it's attractive or repulsive based on the number you end up getting. You don't need to put a negative on there. It's not always an attractive field. Okay. Our last thing, if we're looking for potential energy now, all right, so this is the actual energy that we're getting out of something. If you're taking gravitational potential, it's how much potential energy it's losing as it's coming in, right? How much of that energy is turning into heat and kinetic energy? How much work can be done as this thing moves from one point in a gravitational field to another, okay? And that was UG, right? UG is just phi, that gravitational potential, times the mass. Okay, so if we're looking at electrical potential energy, all right, we're going to use the U still, a little subscript E. All right, our replacement for phi, our replacement for gravitational potential, is electrical potential, which is voltage. So I'm going to put my bars on my V's. And instead of mass, electrical fields are built on charge. All right, now, I don't really like the order that thing's written. I don't know why. It's like sometimes names need to go in a particular order. This one, talking about electrical potential energy, I always think of it as Q times V. I never think of it as V times Q. It just seems weird to me. All right, so I'm going to switch those two. Q times V. Okay, so if you need to find out how much energy you're getting as you move something through a particular voltage, you can use that right there. How much the voltage is changing, that's your V. However much Q is changing, that's your Q, okay? And moving a charge through a voltage, through a potential difference, is doing work. You have to either do work to move it, or it is doing work in moving, all right? Remember, work is the energy being used to move something, okay? So if it's ever asking how much work is being done to move a charge within a certain voltage, using that right there, okay? So, basically, all this stuff is old formulas, but repackaged using different variables. Instead of masses, you have charges. Instead of gravitational potential, you have voltage. Instead of big G, you got big K. All right? But the general process, the actual math involved in moving them around, basically the exact same as when we were dealing with gravitational fields. Okay? So, there's going to be some practice for this. Ask questions. Should I shave the mustache? It'll be too late for you to tell me because tomorrow, Monday, it's November. Can't shave once November starts. Got to decide soon. I really kind of like having a mustache. Whatever. Doesn't matter. See ya.